On August 4th, 2026, NASA sent a command 13 billion miles into deep space and waited, not hours, days. Because at the speed of light, a signal from Earth takes over 19 hours just to reach Voyager 2, and another 19 hours to get any kind of response back. So when engineers at NASA's Jet Propulsion Laboratory executed what they internally called the Big Bang, a high-stakes, all-or-nothing power overhaul performed simultaneously across a spacecraft that is older than most of the people working on it, they had to wait nearly 2 full days to find out if it worked. It worked. And what that means for science, for space exploration, and for what we actually know about the universe beyond our solar system is something that almost nobody outside the space community is paying attention to right now. So let's fix that. Because what Voyager 2 is measuring in interstellar space right now, and what the Big Bang just guaranteed it can keep measuring, is rewriting the textbooks on what exists between the stars. Let's start from the beginning. Voyager 2 was launched on August 20th, 1977. That is not a typo, 1977. The same year Star Wars came out, 4 years before the first IBM personal computer existed, and a decade before the World Wide Web. The spacecraft was built with technology from the early 1970s, designed for a 5-year mission, and has now been operating for nearly 49 years without stopping. To put that in context, the engineers who originally built Voyager 2 are in their 70s and 80s. Some of them have died, and the probe they designed and launched nearly half a century ago is still working, still transmitting, still making discoveries that the scientists monitoring it did not expect. Here's the thing about Voyager 2 specifically that makes it different from anything else humanity has ever built. It is the only spacecraft in history to have visited all 4 outer planets: Jupiter, Saturn, Uranus, Neptune. It made those flybys because NASA launched it on what they called the Grand Tour, a trajectory that took advantage of a rare planetary alignment that only occurs once every 176 years. That alignment let a single spacecraft slingshot from one giant planet to the next, gathering speed and gathering data across the entire outer solar system in a single mission that should have ended in 1982. But it didn't end. And when Voyager 2 flew past Neptune in 1989, becoming the only spacecraft in history to have observed the ice giants up close, it just kept going, outward, into the darkness beyond all the planets, beyond the Kuiper Belt, toward the boundary of the solar system itself. And on November 5th, 2018, it crossed that boundary. The boundary is called the heliopause, and to understand why crossing it matters, you have to understand what the heliopause actually is, because it is one of the most important structures in the solar system, and almost nobody ever talks about it. The sun does not just sit quietly at the center of the solar system producing light, it also constantly blows a wind. Not wind the way Earth's atmosphere produces it, but a continuous stream of charged particles, electrons, protons, helium nuclei that flows outward from the sun in all directions at roughly 1,000,000 miles per hour. This stream is called the solar wind, and as it expands outward into space, it inflates a massive bubble around the solar system, a bubble made of solar particles and solar magnetic fields. That bubble is called the heliosphere. The heliosphere is enormous. It extends far beyond Neptune, far beyond Pluto, far beyond the Kuiper Belt. At its outer edge, the pressure of the solar wind finally meets the pressure of the interstellar medium, the gas and plasma and magnetic fields that fill the space between star systems, and the two pressures balance. That balance point, that boundary between solar space and interstellar space, is the heliopause. Inside the heliopause, the sun's territory, all 8 planets, every moon, every asteroid, every comet we've ever cataloged, every spacecraft humanity has ever launched except for the 2 Voyagers, all of it exists inside that bubble. Outside the heliopause, interstellar space, the actual space between stars, a region that no human-made object had ever entered before Voyager 1 crossed the heliopause on August 25th, 2012. Now here is why the heliosphere matters beyond being a fascinating structure. It shields us. The galaxy is filled with cosmic rays, extremely high-energy particles accelerated by supernova explosions, colliding neutron stars, and other violent events happening millions of light years away. These particles are constantly streaming through the Milky Way, and the heliosphere acts as a partial shield against them. It deflects and slows a significant fraction of the galactic cosmic rays that would otherwise reach the inner solar system and hit Earth. Without the heliosphere, the radiation environment in our solar system would be measurably worse. The sun, by blowing its wind outward, is protecting its own planets without any of them ever knowing it. Understanding how good that shield is, how thick it is, how its shielding power changes over time, how it interacts with the interstellar medium pressing against it from outside, that is not an academic question. That is a question about the long-term habitability of this solar system. And if you care even slightly about whether Earth remains a place that complex life can survive on over millions of years, the answers Voyager 2 is currently transmitting back to Earth matter directly to that question. And the only way to actually answer it is to go there, to physically put a sensor inside the interstellar medium and measure what is there, which is exactly what Voyager 2 has been doing since November 2018. Voyager 1 crossed the heliopause first, in 2012, at a distance of about 121 astronomical units from the Sun. One astronomical unit is roughly 93 million miles, the distance from Earth to the Sun. So 121 astronomical units is about 11.2 billion miles from Earth. When Voyager 1 crossed, scientists got their first ever direct measurements of what the heliopause actually looks like in situ. But there was a significant problem. Voyager 1's plasma science instrument had failed back in 1980 before it even finished its planetary tour. So the most important measurement near what the plasma environment actually looks like at the heliopause crossing and in interstellar space was completely unavailable. Then Voyager 2 crossed, and everything changed. Voyager 2 crossed the heliopause on November 5, 2018, at about 119 astronomical units from the Sun in a different direction than Voyager 1. And because Voyager 2's plasma science instrument was still working, had been working continuously since launch, scientists got what they had been waiting decades for: a direct in situ plasma measurement of the heliopause crossing and the interstellar medium on the other side. The data came back, and it did not match what anyone predicted. The plasma just outside the heliopause in the local interstellar medium registered temperatures between 30,000 and 50,000 Kelvin. Let that land for a moment. The interstellar medium, the space between the stars, was supposed to be cold, quiet, sparse. The models said the local interstellar medium at that distance from the Sun should be relatively cool plasma at densities barely above nothing. What Voyager 2 actually measured was plasma dramatically hotter than the models predicted. Not slightly hotter, not within the margin of error, dramatically hotter. The difference between the prediction and the measurement was the kind of gap that forces scientists to reconsider the model itself, not the measurement, and that was just the temperature. The heliopause itself was not what the models described either. The standard picture was a relatively clean boundary, solar wind on one side, interstellar medium on the other, a sharp transition between them. What Voyager 2 measured was a layered, complex transition zone. Multiple distinct regions where properties shifted gradually rather than a single clean line where one environment ended and another began. The heliosheath, the region just inside the heliopause where the solar wind slows and piles up before hitting the boundary, had a different structure than predicted. The termination shock in the region further inside where the solar wind first slows from supersonic to subsonic speeds was in a different location and had a different shape than the model said it should. Meanwhile, Voyager 1 and Voyager 2 had both now measured the heliopause from two different directions. Voyager 1 crossed going roughly north out of the ecliptic plane. Voyager 2 crossed going roughly south. The two crossings happened at similar distances from the Sun, 119 to 121 astronomical units, which suggested the heliosphere might be more spherical than the old comet-shaped model had predicted. But the two crossings showed dramatically different magnetic field behavior at the boundary. Voyager 1 saw intense magnetic field fluctuations right at the heliopause. Voyager 2 saw almost none. Same boundary, different directions, completely different behavior. Which means the heliosphere is not symmetric. Its properties are not uniform around its surface. The bubble that protects our solar system looks and behaves differently depending on which direction you examine it. And we have exactly two data points of direct in situ measurement to work from. 2. After 49 years of effort and billions of miles of travel, think about that. 2 data points, one in each direction. The entire scientific picture of what the heliosphere's boundary actually looks like from the inside out rests on the combined measurements of 2 spacecraft launched in 1977. And one of those spacecraft right now is still collecting data that contradicts the models and expands what we know. This is the scientific situation that existed going into August 2026. And this is why what JPL announced on August 4th matters so much. Because Voyager 2, right now, in August 2026, still has 3 working science instruments. The magnetometer, measuring the magnetic field of the interstellar mediums, which is not zero. There is a real magnetic field in interstellar space, carried there by plasma ejected by dying stars across billions of years of galactic history, and Voyager 2 is measuring its direction and strength from inside it. The plasma wave subsystem, detecting oscillations in the interstellar plasma that allows scientists to calculate the density of electrons in the medium surrounding the spacecraft. This is the same type of instrument that on Voyager 1 has been detecting persistent plasma wave emissions continuously since 2017, letting scientists map variations in the density of the interstellar medium as the probe moves through it. And the cosmic ray subsystem, measuring the galactic cosmic rays streaming in from deep space, which, from the outside of the heliosphere, directly tells scientists how the sun's shield is actually performing over the solar cycle. The sun cycles through roughly 11 years of activity. Near solar maximum, when solar activity peaks and the solar wind strengthens, the heliosphere inflates slightly and deflects more cosmic rays. Near solar minimum, it contracts and lets more through. Voyager's cosmic ray instruments in interstellar space give scientists the first direct outside-in measurement of that variation, not inferred, not modeled, not observed indirectly through an atmosphere, measured directly from outside. Without the Big Bang intervention, the cosmic ray subsystem was scheduled to be shut off before the end of 2026. Power constraints made it unavoidable, or they did until the JPL engineering team spent months designing a way around it. Here is what the Big Bang actually was in plain terms. Voyager 2 runs on nuclear power. Radioisotope thermoelectric generators, essentially very sophisticated nuclear batteries, that convert the heat from the radioactive decay of plutonium-238 into electricity. When Voyager 2 launched in 1977, those generators were producing roughly 470 watts of electrical power. Every year since, as the plutonium decays, output drops by about 4 watts. After nearly half a century, the power budget is so tight that individual watts determine which science instruments stay alive and which get shut off forever. The team doesn't have the luxury of approximation. Every single watt on this spacecraft has to be assigned to a purpose, and when the power budget shrinks, something has to go. That has meant years of carefully prioritized shutdowns, heaters turned off, backup systems deactivated, science instruments taken offline one by one, in an order agreed upon jointly by the science and engineering teams based on which instruments were still contributing irreplaceable data versus which had effectively completed their scientific purpose after the planetary flybys ended in 1989. To keep Voyager 2's thruster fuel lines from freezing C, which would disable the thrusters, which would make it impossible to aim the antenna at Earth, which would permanently end the mission, the spacecraft had been using 3 dedicated heater devices. These heaters consume power that was now competing directly with the power needed to keep science instruments running. The Big Bang replaced those 3 heaters with 3 alternative thermal management devices that accomplished the same job while consuming almost 10 watts less. A decade ago, 10 watts on a spacecraft would be a rounding error. On Voyager 2 in 2026, 10 watts is the difference between keeping a science instrument running for another year or shutting it down permanently. But the swap had to be executed simultaneously. All 3 heaters off and all 3 alternative devices on at the same instant, not sequentially, simultaneously. Because if the new thermal management devices didn't come online fast enough after the heaters cut out, the fuel lines would begin cooling toward temperatures that could cause irreversible damage before protection was restored. The window for error was essentially 0. There was no retry. If it went wrong permanently. The engineering team spent months calculating and planning. They tested the procedure on Voyager 2 first, chosen over Voyager 1 because Voyager 2 is closer to Earth, meaning the 2-day command and response cycle is slightly shorter, and because Voyager 2 had slightly more power headroom to work with, making it the marginally safer test subject for a procedure that had never been done on a spacecraft at this distance. The test runs during May and June 2026 succeeded. The full implementation succeeded. NASA published confirmation on August 4th, 2026. The result: Voyager 2's 3 science instruments now have enough power to keep running for at least another year beyond what was previously projected, and the same procedure is now planned for Voyager 1 in the coming months. Let that engineering achievement sit for a moment. A team of people, some of whom have worked on this mission for decades, some of whom were born after the spacecraft launched, all of whom have never physically touched the hardware they maintain, designed and executed a simultaneous power systems overhaul on a nuclear-powered spacecraft traveling at 34,000 miles per hour through interstellar space, 13 billion miles away, with a 19-hour communication delay each direction, and they got it right on the first full attempt. No second chances, no undo button. Just careful engineering, careful planning, and a 38-hour wait to find out if the most distant human-made object in existence was still operational. The signals from Voyager 2 arrive at Earth through 3 enormous dish antennas, part of NASA's deep space network located in California, Spain, and Australia, operating simultaneously to collect enough signal to decode the data. Voyager 2's radio transmitter produces 23 watts of power. the same wattage as a refrigerator light bulb. By the time that signal travels 13 billion miles and arrives at Earth, it is so faint that the combined receiving area of the world's most sophisticated antenna network is needed to detect it. The data arrives at a rate of 160 bits per second. For context, that is roughly equivalent to the dial-up internet connections of the early 1990s. At that speed, transmitting a single high-resolution photograph would take hours. Everything humanity knows about the direct in situ conditions of the local interstellar medium comes through that trickle, and it comes through it in a way that cannot be replicated by anything else currently in existence or currently planned. This is the part that doesn't get said clearly enough in most coverage of the Voyager mission. There is no substitute. Every other measurement of the interstellar medium is indirect. Telescopes observe it through the absorption patterns it creates in starlight passing through it. Instruments like the Interstellar Boundary Explorer IBEX measure energetic neutral atoms that stream back toward the sun from the heliopause region. These are powerful tools, but none of them are physically inside the interstellar medium surrounded by it, measuring it from within it. Voyager 2 is, right now, in August 2026, at 13 billion miles from Earth, still transmitting at 160 bits per second, still returning irreplaceable data, and because of the Big Bang, still doing it with 3 instruments instead of 2. The engineering goal following the Big Bang success is to keep Voyager 2's 3 science instruments running through at least 2027. If the hardware cooperates, and it has consistently surprised everyone who works on it, the mission could potentially extend significantly further. JPL has stated that if both Voyagers remain healthy, at least 1 science instrument on each could potentially remain operational into the 2030s. On November 18, 2026, Voyager 1 is projected to reach exactly 1 light day from Earth. 1 light day, a signal sent from Earth at the moment it crosses that threshold will take 24 hours to arrive at the spacecraft, another 24 hours to receive any response. Voyager 1 will be the first human-made object in history to reach that symbolic distance, and it will still be working, still transmitting its own trickle of irreplaceable data from an even further point in the interstellar medium, currently more than 15 billion miles from Earth, so distant that its signals take over 23 hours just to arrive. Voyager 2 won't reach 1 light day until November 2035. Whether it's still operating when it gets there is genuinely uncertain. The most realistic engineering estimates suggest it may not be, but the probe has been defying those estimates for decades. The same team that found a way to swap thermal management systems simultaneously on a spacecraft 13 billion miles away will keep looking for the next solution, the next 10 watts, the next year of measurement. What does it mean for these instruments to keep running? What is actually at stake in the data they send back? Consider what has already changed in how scientists understand the heliosphere just from what Voyager 2 measured at and after its 2018 heliopause crossing. The plasma temperatures were wrong, the boundary structure was wrong, the magnetic field behavior was different in 2 directions in ways the models didn't predict. The helios-heath structure was unexpected. These are not minor calibration errors. These are fundamental discrepancies between the model of the heliosphere that scientists had built over decades and the reality that Voyager 2 found when it actually got there. Now extend that forward. Voyager 2 has been in the interstellar medium since 2018. It has now been collecting direct measurements of the interstellar medium for 8 years. As it moves deeper into the medium, currently traveling at about 34,000 miles per hour, the measurements it takes are from regions of space further from the heliopause boundary. Whether the plasma temperature and density and magnetic field strength and cosmic ray flux change as Voyager 2 moves away from the heliosphere or remains stable, that is not a question that can be answered from Earth. It requires a probe physically moving through the medium and reporting back over time. There is one probe doing that, Voyager 2, and the cosmic ray data being returned by the cosmic ray subsystem, the instrument that almost got shut off before the end of 2026 before the Big Bang extended its life, is feeding directly into models of how the heliosphere's shielding behavior changes over the solar cycle. The sun is currently near the peak of solar cycle 25. How the heliosphere responds to that activity peak measured directly from outside by Voyager's instruments is data that has never existed before because no probe was outside the heliosphere for the previous solar maximum periods. This is genuinely novel science. The first time in history that the heliosphere's shielding effectiveness at solar maximum has been directly measured from outside. Every day the instruments run, data arrives that cannot come from anywhere else. The next interstellar mission, if one is ever funded, approved, designed, built, and launched, would take decades to travel the distances Voyager 2 has already covered. NASA's proposed interstellar probe concept, a next-generation mission designed to reach 1,000 astronomical units over a 50-year mission, has not yet been formally funded or approved. Even if it were funded tomorrow and launched within 5 years, it would not reach the distances Voyager 2 is at right now until sometime in the 2070s. And Voyager 2 is still moving, still transmitting, still measuring. The spacecraft launched in 1977 is, in 2026, still the state of the art for direct interstellar medium measurements. There is nothing newer, there is nothing better, there is nothing that can replace it. The Big Bang bought at least one more year of measurements that would otherwise not exist. It is worth pausing on what kind of object Voyager 2 actually is at this point in its life. It is not the cutting-edge spacecraft it was at launch. It has no camera. Those were shut off long ago to save power. It has no ability to image planets or stars or anything else. It has a magnetometer, a plasma wave detector, and a cosmic ray counter. It is, at its core, a set of sensors attached to a transmitter, attached to a nuclear battery, hurtling through interstellar space at 34,000 miles per hour, reporting its measurements back to Earth one trickle of bits at a time. But the measurements those sensors are taking cannot be found in any textbook. They cannot be downloaded from any database. They are not observable from the ground or from orbit. They exist only because 49 years ago, engineers designed a spacecraft that kept working, pointed it in a direction that eventually led it out of the solar system, and have spent nearly 5 decades keeping it alive, one careful engineering decision at a time. The Big Bang is the latest of those decisions. It is, in the context of the mission's history, both extraordinary and entirely in keeping with what the Voyager program has always been. A story of people finding ways to extend the possible, 1 watt, 1 year, 1 data transmission at a time. On August 4th, 2026, the confirmation came back from 13 billion miles away. The Big Bang worked. Voyager 2 has more time. The interstellar medium has more witnesses. And the universe beyond our solar system, which keeps turning out to be stranger and more complex and more surprising than the models predicted, keeps getting measured by the only thing humanity has ever managed to put inside it. A refrigerator light bulb's worth of radio power traveling 19 hours through interstellar space, carrying data that changes what we know about the place our entire solar system exists within. That signal is not coming from outside our system in any mysterious or unexplained way. It is coming from something we built, something we launched, something we have kept alive for 49 years through careful, patient, extraordinary engineering. And because of what JPL confirmed on August 4th, 2026, it is going to keep coming for at least another year. That is what happened. And it deserved a lot more attention than it got.